Math 1314, Tyler Junior College, Section 3.6, Polynomial and Rational Inequalities. How to solve a polynomial inequality, Example 2. In the previous example, in the previous video, we solved a pretty straightforward polynomial inequality. It was already compared to 0, which was handy when solving the equation version of the problem. It was quadratic and easy to factor. So nothing really got out of control. But in this one, we've got some things we need to work around. The steps aren't going to change. But that first step, well, you'll see. Let's solve x squared times x plus 3 is greater than 4. Step 1, solve the corresponding equation. So we're going to start by solving x squared times x plus 3 equals 4. So how do we solve this? Well, it's a polynomial equation, so we probably want to get it equal to 0 and try to factor. Notice it's already factored, but the factorization is completely useless since it's not equal to 0. Therefore, the useless factorization needs to be destroyed by distributing the x squared to get x cubed plus 3x squared. And why waste a line just to move the 4 over on the next one? We'll move it over now. So now we have to solve x cubed plus 3x squared minus 4 is equal to 0. And although this is a trinomial, it is not a quadratic trinomial. So we can't factor it like the one we did before. There's no GCF to factor out. We can't factor by grouping. This will not succumb to any convenient factoring techniques. Lucky for us, about 2 series of videos ago, we built a new but lengthy technique for factoring larger degree equations when it won't succumb to a previous factoring technique. So yes, we are about to do all the things we did in 3.4. We're going to list the possible rational zeros. We're going to use synthetic division to find a zero that works, and then go on from there. Recall that the possible rational zeros are of the form factors of the constant term over factors of the leading coefficient. Lucky for us, the leading coefficient is 1, and so the only possible denominators are 1 and negative 1. Therefore, we really only need to look at factors of the constant term. Factors of 4 are 1, 2, and 4. Technically, plus minus 1, plus minus 2, plus minus 4. So there's only 6 numbers that might work as a good box number in synthetic division. Let's try 1. That's always a good place to start. What will the top row be? It's the coefficients of the dividend, but be careful. This equation is missing the x term. X cubed, x squared, x to the first. There is no x to the first. No x's at all. So when I set up the top row and start writing my coefficients, I got to remember to put the 0. 1 because of the x cubed, 3 because of the x squared, 0 because it's missing the x term, and then the constant term of negative 4. Hopefully this one will work, otherwise we have to cross it out and try another. Bring down the first number to get a 1, multiply by the box. 1 times 1 is 1. If you're not sure what's going on, go back and rewatch the video series for Chapter 3, Section 4 about finding zeros of rational functions. Finding zeros of polynomial functions. Bring down the 1. 1 times the box number is 1. Add. 4 times the box number is 4. Add. Oh, looky here. 4 times the box number is 4. We got lucky on the first one. Not really, I built the problem that way. So, we found a good synthetic division problem, which means that we have 2 factors. One from the box number, and recall that when you move a number in or out of a factor, it changes signs. So the factor associated with the box number of 1 is x minus 1, and the factor associated with the bottom row will start 1 degree lower than the original equation. Since the original equation was 3rd degree, the quotient will start 2nd degree. This one represents 1x squared. And then plus 4x plus 4. So it didn't take too long, but we factored the left side of this equation. The right side is still equal to 0. And that's good. Oh, and this is a quadratic trinomial, so we can try to factor it. It's not that hard to factor. What two numbers both add to give 4 and multiply to give 4? Add and multiply. 2 and 2. So we have x plus 2 times x plus 2. And when we solve each factor equal to 0, we get x equals 1, and we get x equals negative 2 twice. A multiplicity of 2, if you will. But since these are our boundary points, I don't need to list the negative 2 twice. So in this example, the first step took quite a bit of work. Because solving the equation required us to use some techniques we learned earlier. So let's move on to step 2. Partition the number line into intervals. We only have 2 boundary points, negative 2 and 1, which means we only have 2 intervals. The interval to the left of negative 2 is negative infinity comma negative 2. We have 3 intervals. The middle interval is negative 2 comma 1, and the rightmost interval is 1 comma infinity. From each interval, we select a test point. I need a number to the left of negative 2. Negative 3 will suffice. I need a number between negative 2 and 1. I can pick 0 there. And I need a number to the right of 1. How about 2? Again, your choice doesn't matter as long as it's in the interval. Now that we have our test points, we test them into the original inequality. The original inequality is up here, so we're going to substitute each of these values into it and pass judgment on the results. Starting with negative 3, we have negative 3 squared times negative 3 plus 3, and we're seeing if that's greater than 4. Negative 3 squared is 9. Negative 3 plus 3 is 0. Still comparing that to 4. 9 times 0 is 0. 0 is greater than 4 is a lie. That's false. At this point, we can instantly cross out the interval that the test point came from. All right. Next, x equals 0. This one will be a little bit easier. X equals 0, well, I'm going to get the same results because 0 squared times 0 plus 3, is that greater than 4? The 0 times anything is 0, so the whole left side instantly collapses to 0. We get 0 is greater than 4. That is still false. I want to take this opportunity to dispel a myth. The myth is the intervals alternate between true and false, as they did in the previous video where it went false, true, false. There are certain functions where that is true, but there are certain functions where it is not. So you can't just test the first one and assume that it's going to change after each boundary point. You have to check each one. Now, is there a faster way of checking each one? Yes, but let's just stick with what works and works every time. We got to check this one. And by the way, it's possible this could have no solution. If we cross out every interval and throw away the boundary points, there is no solution. If we check x equals 2, we'll get 2 squared times 2 plus 3. Is that greater than 4? Well, this is easy. 2 squared is 4. 2 plus 3 is 5. 4 times 5 is 20. 20 is greater than 4 is true. So we did get to keep at least one interval. And we don't have to union it with anything. Do we keep the boundary point? Do we keep 1? Well, we did not, because remember that the boundary points were the values that made it equal. This inequality does not permit it to be equal. So our answer is just the interval that we kept, 1 to infinity. I'm going to check the time on this because I may do a real quick follow-up example to this one that won't require us to do any extra work, just some extra thinking. Oh yeah, we haven't even hit the 10-minute mark, and I don't expect this to take more than 90 seconds. Let's say, just for the heck of it, that the original inequality was less than instead of greater than. X squared times x plus 3 is less than 4. How would that change the answer? Now we don't have to redo the first step because it would be the same equation, nor the second step because it would be the same intervals, and therefore not the third step because it would be the same test points. And we actually don't even have to redo the fourth step. The first place where we have to consider the difference in equality is when we were passing judgment after testing each value. Because now instead of saying greater than, all of these would say less than. So if these said less than, which ones would be true? Is 0 less than 4? Yes, keep this guy. Is 0 less than 4? Yes, keep this guy. Is 20 less than 4? No, don't keep this guy. So by reversing the inequality, it basically switches which intervals we keep and which ones we don't. So our answer would have been negative infinity comma negative 2 union negative 2 comma infinity. One more follow-up. This one will take even less time. What if it had said x squared times x plus 3 is less than or equal to 4? So in other words, the previous problem, except I slap on the or equal to. Well, the only difference between these two is that or equal to allows me to keep any numbers that make it equal. What numbers make it equal? 1 makes it equal, but 1's already included in this interval. I'm sorry. This was supposed to be a 1 here. So excited about this one, I wasn't paying attention. So let's go back to what I was saying. If we put an or equal to on here, it won't change anything except whether or not we include the boundary points. We would include both of them because both of them make it equal, and now this one allows it to be equal. So we would have to put a bracket on this one. But it gets a little bit crazier than that because we would have to put a bracket on both of these negative 2's. But if these two intervals both include negative 2, then they kind of join together to make one big interval that doesn't pause at negative 2. Go to negative infinity, negative 2, but don't stop because we're including it. Keep going, and our interval will just be negative infinity, comma 1. So you can see that sometimes the issue is how to write your answer, especially if you have two consecutive intervals that include their common boundary because they join together to make one big interval.